Okay. Hello, guys. In this session, we will be discussing three different techniques of integration. In this session, we will be discussing three different techniques of integration. In this session, we will be discussing three different techniques of integration. And that is the substitution method, number one. Number two, trigonometric substitution. Number three, integration by parts. So that's three different techniques of integration. So we're going to start with the substitution rule. And of course, guys, this lecture is the last lecture of the course. Someone asked me on WhatsApp if we have more topics to cover for this course. This will be the last thing we do for this course. So this lecture will be the last. This is the last lecture of the course. Okay. So let's begin. Let's start with our discussion. So as I said, we're starting with, so this is still integration. All right, this is still integration. So let me put integration on top. This is my top. My main heading is integration because we're still doing integration. So this is so let me just move this, sorry. This is, how do we move this again? Let me just do this. Let's move this. I want to write the heading. So this is integration. So this is the main topic. This is the main topic here. Integration. We're still doing integration. But in integration, as I said, today we are covering three different different techniques of integration. So first, we will start with the substitution method. So let me put that heading here. We're starting with the substitution. So we are starting with the substitution method. We are starting with the substitution method. Okay, we're doing the integration. And the first technique we look at is the substitution method. We're doing the substitution method. All right, so now to show how the substitution method works, we're going to show this through examples. We're going to do examples to show this. So let's do examples to show how does the substitution method work. Let's look at example number one. In example number one, we're integrating from 0 to 1, and we are integrating the following function. We're integrating 3x plus 1 to the power of 5. And we're doing this with respect to x. So we're integrating the function 3x plus 1 to the power of 5 with respect to x, and we're integrating it from 0 to 1. So it's a definite integral. So this is a definite integral. Now, how do we apply the substitution method to evaluate this integral? How do we apply the substitution method to evaluate this integral? Now, you can evaluate this integral without having to use the substitution method. You can, but it's going to take you a while because you would have to expand this because this is 3x plus 1 to the power of 5. You would have to expand it, and after expanding it, you then have to integrate each term. So we have to expand it, and then you would have to integrate each term. And I'm sure some of you can see that to expand this, because it is a binomial, so to expand 3x plus 1 to the 5, you can even apply the binomial theorem. You can apply the binomial theorem to expand this, and which will make it simpler for you to expand. And then after expanding it using the binomial theorem, you go ahead and you apply this. You integrate each term. So you can expand it and then integrate it. So you don't have to use the substitution method for this particular problem. You can expand it and then integrate it. But since we are discussing the substitution method, we will use the substitution method. So since we are discussing the substitution method, we'll specifically use the substitution method to evaluate this integral. So how do we do that? How do you use the substitution method? All right. Now, since this is a definite integral, we're going to do the following. Okay, as I was saying, guys, since this is a definite integral, we're going to do the following. We are going to start by evaluating the indefinite integral of the same function. So we'll do like this. We'll go integral of 3x plus 1 Okay, so we start off by integrating the indefinite integral, which is the integral of 3x plus 1 to the power of 5 with respect to x. So we start with this. And then we do the following. Okay, we let u be equal to the following. We let u be equal to the following. We let u be equal to 3x, okay, 3x plus 1, all right? So we let u be equal to 3x plus 1, and this is how the substitution method works, okay? You let u be equal to 3x plus 1. So you let this u be equal to the to what's inside the bracket here, which is 3x plus 1, all right? And then after you do that, you differentiate this u with respect to x. So you do the following. You go, the derivative of u with respect to x is equal to the following. So now you go ahead and you differentiate this 3x plus 1 because that's what u is, because you let u be equal to 3x plus 1. So you go ahead and you differentiate the 3x plus 1 with respect to x. You go ahead and you do that. So the derivative of 3x plus 1 with respect to x is equal to, so you differentiate each term of this, obviously. So the derivative of 3x is just 3, plus the derivative of 1, which is 0. So you get 3, all right? So you differentiate u with respect to x, and that gives you 3, all right? So now let's see what we have. So we say, therefore, the derivative of u with respect to x is equal to 3. Okay? All right? Okay? And then what do we do? So now we let u be equal to, okay, let me go back. We let u be equal to 3x plus 1. And then after we did that, we differentiated u with respect to x, and we got 3. So then what? How does this now help us evaluate the integral? Okay, how does this help us evaluate the integral? Again, how does this help us evaluate the integral? So what we do next is the following. So we can see we've got du dx is equal to 3. So what we're going to do now, we are going to write dx as the subject of this particular formula here. All right, we are going to write dx. We're going to write this dx as the subject of this formula here. I'm going to say that again. We are going to write dx as the subject of this formula here. All right, we are going to write dx as the subject of this formula here. That's what we're going to do. So how do we do that? We do the following. So we say this implies this. This is the same thing as the du is equal to 3 dx. What did we do? We basically multiplied throughout by dx. So we multiply by dx on this side, and we multiply by dx on this side. So these two dx's cancel out, and we end up with this. We end up with du is equal to 3 dx. So that's what we do first. And then what? And then what? And then after we do that, we do the following. We divide both sides by 3, and that gives us 1 over 3 du is equal to dx. Okay, so 1 over 3 du is equal to dx. So now we've made dx the subject of the formula. So dx is equal to a third du. All right. So how do we use this for substitution, for the substitution method? Like how do you use this to now evaluate the integral? Well, we do the following. So as I said before, we are starting with the indefinite integral. Okay, we are starting with the indefinite integral. So we are starting with this integral here. All right, we are starting with the indefinite integral here. So before we go ahead and evaluate the definite integral, we start with the indefinite integral. Let me just see, something is wrong here. Just need to fix this. Let me just fix fix my, okay, I think, okay, wait. Anyway, so as I said, guys, we are starting here. We are starting with the indefinite integral, okay? We are evaluating that first. So let me just go back to where we were before. Now we're here. Okay, so now we say, therefore, now that we've done all of this, we say, therefore, the indefinite integral, which is the indefinite integral of 3x plus 1 to the power of 5 with respect to x, okay, the indefinite integral. I'm going to say this again. The indefinite integral of 3x plus 1 to the power of 5 is now equal to the following. So we say it's equal to the following integral. It's equal to the integral of the following. Now we replace everything with a u. When I say everything, I'm talking about the relevant things. I'm talking about the following. We said that let u be equal to 3x plus 1. Let's just go back to see that. We said let u be equal to 3x plus 1. So we're going to replace 3x plus 1 with a u. Okay, let's go back. We're going to replace this 3x plus 1 here with a u. So in place of 3x plus 1, we put a u to the power of 5 with respect. But now, wait, before we do that. So firstly, we replace the 3x plus 1 with a u. And this is because we said that let u be equal to 3x plus 1. So we replace 3x plus 1 with a u. Okay. So again, and then we go to dx. What did we see with the dx? What is dx in terms of u? We already established, we already found what dx is in terms of u. Dx is equal to 1 over 3 du. We saw that, okay? So dx is equal to 1 over 3 du. So again, we go ahead and we replace dx and write it in terms of du, which is 1 over 3 du. So in place of dx, we put 1 over 3 du. In place of 3x plus 1, we put u. All right? So that's how you then substitute. That's how the substitution rule works. You do that. You do it in this way. So now that you've substituted, and then now you have an integral just in terms of u, you go ahead and you solve. So how do you do that? You take out the 1 over 3 because it's a constant. So take out the 1 over 3 because it's a constant. Now you are left with the integral of u to the power 5 with respect to u. Okay. So what is that integral? What does it equal to? Well, you know your integration rules. Okay, you know your integration rules. If you're integrating u to the power 5, that will give you the following. That is equal to u to the power 5 plus 1 over 5 plus 1. Okay. Now, if you're evaluating an indefinite integral, usually you put a plus c. Okay, you would usually put a plus c here. But since this indefinite integral is a means to an end to evaluate a definite integral, you do not put the plus c, because this indefinite integral we are evaluating is just a means to an end to evaluate a definite integral. Okay, so the real integral we're evaluating is a definite integral. So, but we have to first evaluate the indefinite integral. So because of that, because this indefinite integral is just a means to an end, we do not put a plus c here. We don't put a plus c there. We leave it out. Okay, so now we've got 1 over 3 multiplied by u to the 5 plus 1 over 5 plus 1, which is the same as 1 over 3 multiplied by u to the power 6 over 6. 6 times 3 is 18. So now you've got u to the power 6 over 18. Okay, so u to the power 6 over 18. All right, let's write that in the next page. So we say, therefore, the indefinite integral of 3x plus 1 to the power of 5 with respect to x, the indefinite integral of 3x plus 1 to the power of 5 with respect to x is equal to the following. It's equal to, as we saw in the previous page here, it's equal to u to the power 6 over 18. But then we have to leave our answer. Okay, we have to write down our answer. We have to write our answer in terms of x, because we're working with x's. Okay, so meaning that now we're going to replace the u. Now that we have the answer to this indefinite integral, we will now replace the u with the original, with what we said u is. Okay, and what we said u is, we said u is equal to 3x plus 1. Let's go back and check that. We said u is equal to, u is equal to 3x plus 1. So now we now replace the u in the answer with the 3x plus 1. Okay, so this is now equal to the following. So that's equal to, this is now equal to, this is now equal to 3x plus 1 to the power of 6. And we divide, of course, we divide this by 18. So it's 3x plus 1 to the power 6 divided by 18. So now that's the answer of this indefinite integral. That's the answer of this indefinite integral. Again, I'll say it again. That's the answer of this indefinite integral. I'll say it again. That's the answer of this indefinite integral. But then as I said before, we are evaluating this indefinite integral as a means to an end to evaluate the definite integral of this function, which is the integral from 0 to 1. So now, since we have the indefinite integral, we can now go ahead and evaluate the definite integral. So we basically say the following. We say, therefore, now the definite integral, which is from 0 to 1, of the same function of 3x plus 1 to the power of 5 with respect to x is now equal to the following. It's equal to the function, okay, it is equal to the function that we differentiate to get this. Okay, so basically it's equal to it's equal to this function here. But we've got the answer. It's equal to the indefinite integral, which is this one here. But then we evaluate it from 0 to 1. So now the definite integral of 3x plus 1 to the power 5 with respect to x is equal to the indefinite integral of this same function, which is 3x plus 1 to the 6 over 18, evaluated from 0 to 1. Okay, meaning that it's equal to this. Okay, it's equal to this. It's equal to the following. It's equal to 3x plus 1, which is the indefinite integral of this function. So it's 3x plus 1 to the 6 over 18. And we go ahead and we evaluate this, okay, from 0 to 1. And how do we evaluate it? We've been through this before. We've been through how you evaluate. We've been through how you evaluate, or how we evaluate. Let me just hide this thing. This thing is distracting me. I'm gonna just hide it. Okay, let's hide it. But now it took away my hiding it now took away my thing, my pen. Let me just see how to get it back. So here it is. Okay, so let me just get back to what I was saying. So now here it is, guys. That's what we have here. That's our definite integral. So the definite integral of this function is what we have here. Okay, so now we just basically go and evaluate it. And we've been through this before. Obviously, we've done definite integrals before. So how to evaluate this? We do it the following. You got 3 multiplied by 1 plus 1. So it's 3 times 1 plus 1. And we put this to the power 6. So it's 3 times 1 plus 1 to the power 6. And we divide this by 18. So it's 3 times 1 plus 1. 3 times 1 plus 1 to the power 6 over 18 minus 3 times 0 plus 1 to the power 6 divided by 18. Okay, so that's what we have. So we got 3 times 1 plus 1 to the power 6 divided by 18 minus 3 times 0 plus 1 to the power 6 divided by 18. So that's how you basically evaluate a definite integral. Or that's how you yes, that's how you evaluate a definite integral. Exactly. So now when you work this out, you find that it's equal to the following. So it gives you 455. It gives you 455 divided by 2. So it gives you 455 divided by 2. So that's what it gives you. So this is how you evaluate an integral using the substitution rule. That's the first example. Let me go back. So guys, just go ahead. We are recording this. We are recording this. So if you wanna if you wanna go through it again, you can just rewind the recording, and then you can go ahead and go through the explanation again of how this works. But I'm gonna now move on to the next. I'm gonna now move on to the next example. Okay, I'm gonna go to the next example. Let's go then to the next example. Let's go to the next example and see how this works. Now, in the next example, let's see how this works. This is now example 2, okay? Again, we are going to evaluate a definite integral, okay? And this integral is the integral of the function x multiplied by 2x squared plus 1, okay? Okay, square rooted. So it's the integral from 0 to 2 of x times 2x squared plus 1, okay? Again, let me say it again. It's the integral from 0 to 2 of x times the square root of 2x squared plus 1. It's the square root. So integral from 0 to 2 of x times the square root of 2x squared plus 1. And we are integrating this with respect to x. So we're going to use the substitution rule again to evaluate this integral. Okay, we'll use the substitution rule to evaluate this integral. So now we're going to start by evaluating the indefinite integral of this function. So we're going to start with this. Let's do it. Let's integrate indefinitely the function x times the square root of 2x squared plus 1. Okay, with respect to x. So now we're doing it indefinitely first. So the first thing we do, guys, we let u be equal to 2x squared plus 1. And when we do that, we go ahead and we differentiate this u with respect to x, and let's see what we get when we do that. When we do that, we of course differentiate this because that's what u is. We said let u be that, so let's differentiate that, and that will give us the following: the derivative of 2x squared is going to be 4x plus the derivative of 1, which is 0. So du dx is equal to 4x. And next thing you want to do is you want to write dx as the subject of the formula of this formula here. Okay, so let's go ahead. Multiply it throughout by dx, meaning that you go dx multiplied by the left, and you go dx multiplied by the right. These two dx's will cancel out, and on the left you'll be left with du. On the right you'll be left with 4x dx. Okay, that's how it works. So that's how it works. That's how it works. All right. And now we've got du is equal to 4x dx. So to write dx as the subject of the formula, we divide both sides by 4x. And we are left with 1 over 4x multiplied by du, which is equal to dx on the right. Because we divide both sides by 4x. So the 4x cancels out on the right side. On the left, we have 1 over 4x du, which is equal to, now on the right, we are left with dx. So that's what we have. So now to move forward, we do the following. Okay, we now write we write the integral again, and then we go and substitute. So we do the following. We say, therefore, the integral or the indefinite integral of the function x multiplied by 2x squared plus 1. So the indefinite integral of this function is equal to the following. It's equal to the integral. Now we're going to substitute the u. We said that u is 2x squared plus 1. So we do that, we substitute, okay? And we said that dx is equal to, dx, we said, we saw that dx is 1 over 4x du. So let's substitute. So over here, we've got x here. This is x over here. Okay, that's the x over there. So let's write it down. And then let's write down the following. We've got the square root of 2x squared plus 1, but we said 2x squared plus 1 is u. So we replace that by u. And then over here, we've got dx, but dx in terms of u. Dx in terms of u, as we saw, is 1 over 4x du. Okay, so we substitute it. Okay, as we saw here, we saw that dx is equal to 1 over 4x du. Okay, so then we substitute in place of dx, we put 1 over 4x du. And then when we do that, we can see that we have an x at the bottom and an x at the top. So the two x's will cancel out like this, and we will be left with the integral of the square root of u, okay, multiplied by 1 over 4 du, because the x's cancel out, because the one x is at the top and the other one is at the bottom. So now we are left with the integral of the square root of u times 1 over 4 du. Okay, so moving forward, we factor out the 1 over 4. So we factor out 1 over 4, and inside we are left with the square root of u with respect to u. Now the square root of u can be written as u to the half. So that's the same thing as 1 over 4 multiplied by the integral of u to the power half with respect to u. Okay, so again, applying one of our rules of integration, this integral is equal to u to the half plus 1 divided by half plus 1. Again, this is a means to an end to evaluating a definite integral. So therefore, we're not going to put a plus c here. We're not going to put this plus c, okay? And we go ahead and we evaluate. Okay, so now, how do we evaluate this? Well, we've already evaluated. We've got a quarter times u to the half plus 1 over half plus 1. So this is the same thing as a quarter it's the same thing as a quarter times u to the, now half plus 1 is a 3 over 2, right? So you put this over 3 over 2, okay, like that. Now this is the same thing as now 4 times 3 over 2. You know, you can just multiply the 4 and the 3 over 2, and I mean that's it's the same thing as the 2's will cancel out with the 4, and you have 2 times 3, which is 6. Or you can flip the 3 over 2, you get 2 over 3 times 4, which is 12. And then there's 6 times 2 at the bottom, will cancel out. You'll get 1 over 6. But ultimately, whichever way you do it, this will give you it'll give you a 1 over 6. It'll give you a 1 over 6 multiplied by u to the power 3 over 2. Okay, it'll give you a 1 over 6 multiplied by 3, 1 over 6 times u. It'll give you a 1 over 6 times u to the power of 3 over 2. All right, 1 over 6 times u to the power of 3 over 2. Now we said that u is equal to 2x squared plus 1. Now we have to write it again in terms of x, because now that's the answer. That's our answer. So we have to write the answer in terms of the original variable, which is x. So we said that let u be equal to 2x squared plus 1. So u is 2x squared plus 1. U is equal to 2x squared plus 1. So we replace it here in the answer. So that is the same thing as the 4. It's 1 over 6. 1 over 6 multiplied by 2x squared plus 1 to the power 3 over 2. Okay, so that's the answer to this. Now we've got the indefinite integral. That's the indefinite integral. Now we can go ahead and evaluate the definite integral. That's the indefinite integral. We can now go ahead and evaluate the definite integral. So I'm saying, therefore, the indefinite integral of x multiplied by the square root of 2x squared plus 1 with respect to x, the indefinite integral of that is equal to 1 over 6. Okay, it's 1 over 6 multiplied by 2x squared plus 1 to the power, okay, to the power of 3 over 2. So that's the indefinite integral of this. Now, therefore, the definite integral, which is from 0 to 2 of the same function, which is x multiplied by 2x squared plus 1 with respect to x, the definite integral of this is equal to this indefinite integral, which is 1 over 6, multiplied by 2x squared plus 1 to the power of 3 over 2. Now we evaluate this from 0 all the way to 2. Okay, we evaluate this from 0 to 2. All right. So let's go ahead and evaluate it. So this is the same thing as the following. This is 1 over 6 multiplied by 2 squared plus 1 to the power of 3 over 2 minus 1 over 6 multiplied by 2 times 0 to the power 2 plus 1 to the power 3 over 2. So if you evaluate this, if you work this out in your calculator, you then find that this is equal to the following. It's equal to the following. So the first term here is none of us 2 minus 1 over 6. It's the second term. And that is equal to the following. So this is, when you work that out, you get 13 over 3. So that's the answer to this definite integral. That's the answer for this definite integral. So now we've got so basically, guys, that is how the substitution rule works. You see, that is how the substitution rule works. That is how the substitution rule works. We've looked at 2 examples already, and we can look at another let's look at the last example. Let's look at the last example on the substitution method. This is the substitution method of integration. I know we have a substitution rule we've got a substitution rule in differentiation, but this over here is the substitution method for integration. All right, so don't confuse the two. So now we're integrating from 0. We are integrating from 0 to power 3. Integrating from 0 to power 3. And we are integrating the function 2 multiplied by sine. So this is a trig function now. It's 2 times sine of 3t plus pi over 4. Okay. 2 multiplied by sine of 3t plus pi over 4. We're integrating with respect to t. Okay. So that's our integral. Now, again, for this one, we're going to use the substitution rule. And in this case, we're going to let u be equal to what's inside sine, which is 3t plus power 4. So let u be equal to 3t plus pi over 4. Let u be equal to 3t plus pi over 4. And when you do that, now you're going to differentiate u with respect to t. So du dt is equal to the following. So let's differentiate u with respect to t, meaning that we differentiate 3t plus power 4 with respect to t. Differentiate 3t with respect to t, that will give you 3. And you differentiate power 4, it will give you 0. So the answer here, therefore, is 3. Okay, du dt is 3. We're going to write dt as the subject of the formula. Multiply it throughout by dt first, so you got dt times dt. dt on the left times dt on the right. And these 2 dt's will cancel out. Okay, so therefore you'll get the following. Therefore, you'll get the following. You'll get that du is equal to 3 multiplied by dt. And then next, you are going to divide both sides by 3, and that will give you a 1 over 3 multiplied by du is equal to dt. So that's what that's going to give you. And then now that you did that, you now go ahead and you evaluate the indefinite. You start with the indefinite integral first. You evaluate the indefinite integral of this function 2 multiplied by sine of the function 3t plus pi over 4 with respect to t. So now we first start with the indefinite integral. And that is the same as the following. That's equal to the integral of, now we're going to say 2, now we're going to substitute in the u now. We're going to substitute. Remember, this is the substitution method. So it's 2 times sine. In place of 3t plus power 4, we just simply put u, because we said let u be equal to 3t plus power 4. So we just put u here. So we got 2 sine u, and in place of dt, we're going to put this, because that's dt in terms of u. So we're going to put that. So that's basically was 1/3 du. And then now we got 2 over, basically this is 2 times 1/3 is 2/3. And that's a constant. So we just take it out. So outside now we are left with 2/3 multiplied by the integral of sine u with respect to u. Okay, so outside we got 2/3. And now we integrate sine u. Now, what did you differentiate to get sine u? What is it that you differentiated to get sine u? If you differentiate minus cos u, the thing is, if you differentiate cos u, the derivative of cos u is minus sine u, meaning that to get a positive sine u, you differentiate minus cos u. So over here, then your integral is minus cos u, because you differentiate minus cos u to get sine u, and that is what you get. Minus, and again, you don't put a plus c here, because we are the main integral is a definite integral. All right, so this is equal to the following. So it's equal to minus 2/3 multiplied by cos u. But then u, okay, but then u is basically, u is 3t plus power 4. We replace it. So this is minus 2/3 multiplied by cos of u. Now u is basically just 3t plus pi over 4, like this. So that's the indefinite integral of this function. So now that we have the indefinite integral, we can go ahead and calculate the definite integral. So we say, therefore, the definite integral of this function from 0 to pi over 3 is the following. So it's, the definite integral from 0 to power, the definite integral from 0 to power 3 of this function, which is 2 times sine of 3t plus pi over 4. So it's 2 times sine of 3t plus power 4 with respect, sorry, let me just go back. With respect, so it's the integral of 2 times sine of 3t plus power 4 with respect to t from 0 to power over 3. Okay. Now we saw that the indefinite integral of this is let me go back and see what it is. It's minus 2/3 times cos of 3t plus power 4. So we write that down. It's minus 2/3 multiplied by cos of 3t plus pi over 4. Okay, and we integrate this from 0 to pi over 3. Integrate from 0 to power 3. Okay, this is equal to the following. All right, it's equal to minus 2/3 multiplied by cos of 3 of pi over 3. So we just substitute power 3 plus pi over 4. Okay, so it's this over here minus the following, minus 2/3 multiplied by cos of 3 multiplied by 0 plus pi over 4. Okay, so that's what we have, right? So it's this bracket minus this bracket. When you work it out using a calculator, you get to the answer of the following. Am I touching? Sorry, I touched the wrong thing. Let me just go back. Now this is equal to the following. So this is equal to 2 multiplied by the square root of 2 divided by 3. So that is basically the answer that we get when we evaluate this particular integral. So now, guys, now I'm sure now you can see how the substitution rule works. I'm sure now you have the hang of how the substitution rule works. You got the hang of it. Okay, please practice that. I'm going to give you guys one last tutorial. I've decided already that I'm not going to give you a tutorial test, but I think because of the changes in the timetable, because of the changes in the institutional timetables, you saw the changes in the timetable. If you didn't see it, I'm going to post it on WhatsApp. I'm going to post that on WhatsApp so you can see the changes. Okay, I'll post on WhatsApp and Blackboard the changes which come from the department because of the strike. I think because of all these changes, we can maybe have one more tutorial test. Okay, because of these changes, maybe we can have one more tutorial test. I'm not sure. I'm going to see. I'll see. So I was thinking maybe because of these changes, we can maybe have one more tutorial, and then after that have one more tutorial test. But I'll see. Okay, I think, or we could just leave it at 3 tutorial tests. I have no problem with 3 tutorial tests, but I definitely will give you one last tutorial. Okay, so we don't have to do a 4th tutorial test, but we can, but we are going to do a final tutorial. I'm going to give you guys a tutorial on this particular work here. So I will give you a tutorial on this work here, but we don't have to do a tutorial test, okay, because of what we decided before. So it's up to you guys if you want to do a tutorial test like the last one, or if you want to just not do another tutorial test. But we will definitely do a tutorial. We'll have a last tutorial for this course, which will cover these 3 integration techniques that we're discussing now. So guys, let's go ahead then and see what we have. Okay, let's go ahead and see what we have. Okay. Okay. So let's go to the next thing. Now the next thing is the next integration technique. Okay, it's the next integration technique. So that the next integration technique is the trigonometric substitution. So we've done the substitution rule. Now let's look at trigonometric substitution. Trigonometric. We're looking at trigonometric substitution. Okay, wait, let me just go back there. Sorry. Let's look at trigonometric this is trigonometric substitution. This is called trigonometric substitution. So let's look at this trigonometric substitution and see what we have. So we look at trigonometric substitution. All right. Now, again, we're going to show how this works through examples. We're going to show how this works through examples. Let's look at example 1. Okay, we're going to use trigonometric substitution. Trigonometric substitution. Now, let's say we have the integral of cos squared t with respect to t. It's a trigonometric integral. Now, I'm going to give you guys formulas that you guys are going to use. I will give you the formulas to use for this work, okay? So for example, for this one, you can see already, this is a trigonometric integral. And as you can see by the looks of it, it doesn't look like you're going to use it. It doesn't look like an integral that you evaluate with the substitution rule. It doesn't. If you look at all the examples we looked at for the substitution rule, there's always a function inside, you know, another function that shows you that, okay, this is the substitution rule. This is the problem for the substitution rule. All the ones we did for the substitution rule, you see that there's always some function within a function that we have to let u be equal to, you know. But this one that we have here, you can see that we can't use the substitution rule here. There's no function within a function. We just have a trigonometric function, and it's cos squared t, okay? Now, in this case, you go look at the formula sheet because I will provide the formulas for you guys. Go look at the formula sheet. If you go look at the formula sheet, you will see an identity. Okay, go look at the identity that corresponds to this. Go look at the formula sheet, and in the formula sheet, you're gonna see an identity. Okay, you will see an identity that corresponds to this. Integral. So basically, you find a suitable identity. That's what you do. You go ahead and you find a suitable identity to evaluate this. Okay, you go and find a suitable identity to evaluate this. All right, let's see. Okay, guys, I'm back. Okay, so guys, as I was saying, we have to go and find a suitable identity for this, okay, in the formula sheet that I will provide for you guys. Now, if you go to the formula sheet, you'll see a formula that looks like this. Okay, cos squared t is equal to 1/2 or half multiplied by cos of 2t plus 1/2. So that's the identity we use for this one. This will be provided for you in the formula sheet. Okay, so it's simple to see which one we use because we've got cos squared t. So then we say, okay, therefore, we use that identity. We say, therefore, that is equal to, this integral here is equal to the following. And it's an indefinite integral, as you can see. So we substitute it. In place of cos squared t, we replace that with a half multiplied by cos 2t plus a half. So we replace the cos squared t by this. Okay, we do this with respect to t. And then obviously we're going to integrate each of these terms. So this is the same thing as the integral of 1/2 multiplied by cos 2t with respect to t plus the integral of 1/2 with respect to t. So we've got the integral of half cos 2t. We've got the integral of half cos 2t with respect to t plus the integral of half with respect to t. So we integrate each term. And now let's start with the first integral. Let's start with this one here. Let's integrate this one here first because we have to integrate each of these. So let's go ahead and integrate that one first and see what we get. Let's go to the next page. So we say, therefore, the integral, okay, of half cos 2t, half cos 2t with respect to t. So the integral of half cos 2t with respect to t is equal to the following. You take out the half because it's constant. You integrate in cos 2t with respect to t. Now you have a function here within the function. You got 2t, you got cos 2t. So this one, it looks like an integral where you can apply the substitution rule. So in this case, you're going to go ahead and you're going to say let u be equal to 2t. And of course, you're going to differentiate u with respect to t. And that's going to just give you 2, because the derivative of 2t with respect to t is just 2. Again, you go ahead and you write dt as the subject of the formula, and that will give you a 1/2 du is equal to dt. And you go ahead and you substitute. So you're going to say, therefore, the integral of cos 2t with respect to t is equal to the integral of the following. So you substitute, you go cos of u, because 2t is u, and multiply this, of course, this is multiplied by 1/2, and of course, multiply by du. Because, so you replace dt with 1/2 du, and you replace 2t with the u, and you get this. So now you basically just factor out the 1/2 is a constant, the 1/2 outside, and inside you got the integral of cos u with respect to u, cos u with respect to u. So now you got a half outside. Now the integral of cos u with respect to u. So you ask, what did you differentiate to get cos u? You differentiated sine u. So then this will be sine u. It'll be sine u. But then because there's you have to add this to another integral. We don't put as plus c yet. We don't put a plus c yet. This is the same thing though as 1/2 multiplied by sine of. Now we said u is 2t, so this is sine of 2t. Okay, by sine of 2t. You can put a bracket here to show that it's sine of 2t. So we don't confuse it with multiplication. So that's what it is then. And then but then that's the integral of cos t, the integral of cos t with respect to t. Now, the integral of half cos t with respect to t, we have to multiply by the half outside. So we say, therefore, half of the integral of cos 2t with respect to t is equal to the following, because there's a half outside there. Half of the integral of cos 2t with respect to 2t is equal to 1/2 sine 2t. So it's half multiplied by 1/2, or by half multiplied by sine 2t. is this. So you multiply the half with a half, you get a quarter. So now you have 1/4 multiplied by sine of 2t. So now we have the integral of the first term there. We have the integral of the first term there. Okay, it's a quarter times sine 2t. Now, what is the integral of the second term? And now the second term is the second term is this one here. It's the integral of half dt. What is the integral of half dt? Again, I'll say it again. What is the integral of half dt? Again, I'll say it again. What is the integral of half dt? Well, let's work it out and see. We've got the integral of half cos 2t now, but now we want to know what is the integral of half dt. The integral of half dt is simply half t. The integral of half dt, because half is a constant, so the integral of half dt is just simply just half t. Okay, again from the integration rules. So therefore, we have the following. Okay, therefore we have that the integral of cos squared t with respect to t is the following. Now we've got both terms. So say therefore the integral of cos squared t with respect to t is equal to the following. It's equal to the integral. Let's go back again. It's equal to this integral here plus this integral here. Now this integral here, the half cos 2t dt is so it's equal to a quarter sine 2t. Okay, so it's a quarter multiplied by sine 2t. And we add this to the integral of the second integral there, which is a half dt, and that's a half t. All right, guys, so as I was saying, so therefore we can see that the integral of cos squared t dt is equal to a quarter sine 2t plus half t, all right? And that since this is a final answer, we can then put a plus c here because we're dealing with an indefinite integral. So since this is the final answer, we can put a plus c at the end. So we got a quarter sine 2t plus a half t plus a c because we are dealing with an indefinite integral. And this is the final answer, okay? So again, guys, you can go through this again to see how it works again. If you miss something, if there's something you don't understand, go through the recording again to see how it works. This is a trigonometric substitution. You have an integral of a trig function, and you can't use the substitution rule. Then you use the trigonometric substitution, meaning that you have to go to the formula sheet and you have to go look and see which trigonometric identity can you apply in order to evaluate this integral. And in this case, this is the trigonometric identity that we used. Is this one here. This one here. Okay, and then you go ahead and you substitute and you evaluate, like we did in this example. So let's go to the next one. Let's go to another example of this. Okay, let's look at another example of this. All right, let's look at another example of this. Let me just find the example. Let's look at another example of this where we look at a problem where we have to use trigonometric substitution. Okay, let's look at example 2. Let's look at example 2 of this. Okay, example 2. All right, now example 2, we have the integral from 0 to pi over 2 of sine squared x with respect to x. Okay, so now again we have a trigonometric function Okay, again, we have a trigonometric function, and we can see here that we cannot use the substitution rule here. So therefore, again, we go to the formula sheet, we go find a suitable identity to apply here in order to evaluate this integral. So you go again, I will provide you guys with this trigonometric identities in the formula sheet. Okay, so we go to the formula sheet and we find this one. We go look and we see that we have a trigonometric identity that looks like this. We got sine squared x is equal to 1/2 minus 1/2 cos 2t. So you go to the formula sheet and you find this identity here. You have sine squared x is equal to, okay, now I have t, sorry. I don't know why I have t here. Okay, let me just change everything to t, sorry. Okay, so let me just go back and just, let's make this example with a t. Let's make this with a t. So this is sine squared t, and this is dt, right? So you go to the formula sheet, and you're going to find an identity that this particular identity, sine squared t, is equal to half minus half cos 2t. And that's the one you use for this particular integral, as you can see. So again, now in this case, we have a definite integral. But first, we are going to start by evaluating an indefinite integral. We're going to start by evaluating, we will start by evaluating the indefinite integral sine squared t with respect to t. The integral, the indefinite integral of sine squared t with respect to t. We'll start there. Before we evaluate the definite integral, we need the indefinite integral first. So let's go ahead and do it. Now, we substitute this using this identity. We substitute by using this identity. All right, so now we're evaluating this indefinite integral by using this trigonometric substitution. So in place of sine squared t, we're gonna put half minus a half multiplied by cos 2t. Okay, we do this with respect to t. All right, we go half so in place of sine squared t, we've got half minus half cos 2t. Okay, in place of sine squared t, we substitute half minus half cos 2t. All right. All right. So now we obviously just integrate each of these terms. So this is the integral of half with respect to t minus the integral of half multiplied by cos 2t with respect. Wait, let me go back. Cos 2t with respect to t. Okay. So now this is what we have now. So now we have to integrate this over here and also integrate this. But then by the looks of it, we've already done these integrals in the previous example. So we saw that the integral, let me just go back. So we don't have to go ahead and evaluate this. We don't have to go ahead and do it again because we've done it already. So the integral of half dt obviously is half, it's half t. Okay, so we go minus, and the integral of half cos 2t. We saw that the integral of half cos 2t is the, let me just go check. The integral of half cos 2t, we saw that to be, wait, let me, okay. The integral of half cos 2t is equal to 1/4 sine 2t. 1/4 sine 2t. So we've got 1/4 sine 2t. Okay. The integral of half cos 2t is equal to 1/4 sine 2t. Okay. All right. Let me just write it down here quickly. Right. Okay. Okay. So it's a half t minus a quarter sine 2t, right? Quarter sine 2t. Okay, that's it. And then we're gonna put a plus c because it's an no, not in this case. So in this case, we don't put a plus c here. The reason for us not putting a plus c here is because we are dealing with a definite integral. So this is just the means to an end to evaluating a definite integral. So the indefinite integral of this function is half t minus a quarter sine 2t. So then to evaluate the definite integral, we use the indefinite integral. So we're gonna say the following. So now we say the following. We say therefore, the definite integral of this function from 0 to pi over 2, okay, of sine squared t dt, the definite integral of this function is equal to the following. It's equal to half t minus 1 over 4 sine 2t. Okay, so that's the indefinite integral inside the bracket, and then we evaluate this from 0 to pi over 2. Okay, then we go ahead. Now to evaluate, obviously we just substitute. Okay, we evaluate, we just substitute. We go ahead. We say 1 over 2. Multiply this by pi over 2 minus 1 over 4 times by sine of 2 times pi over 2. We put this in a bracket. Say minus. Again, we go we go ahead and we say 1 over 2, substitute 0, or minus 1 over 4 times by sine in place. Okay, sine 2 times by 0. Okay, we'll close this, and then we basically work this out. So now we got this minus this bracket. Work it out, and then you find that you just end up with power of 4. So this is just equal to power of 4. Power of 4, that's the answer. So this is the answer to this definite integral. So here, we used trigonometric substitution. Now, trigonometric substitution is it's straightforward. It's pretty straightforward. You just use you use the trigonometric identities. So if you look at an integral, you see that you cannot use integration by the substitution method. Then, and if you say trigonometric function, then just go ahead and use trigonometric substitution. Use trigonometric substitution. All right. So now let's go look at something else. Let's look at the last part of this lecture, which is integration by parts, which is the third and the last integration technique we're going to look at. Okay, integration by parts. So integration by parts is the third and the last integration technique that we look at in this course. Again, as I said, this is the last lecture of the course. After this, I'll give you guys a tutorial. Okay, so this is integration by parts. Integration by parts. Integration by parts. Integration by parts is an integration technique, and it's the last integration technique that we look at in this course. So integration by parts is the last integration technique that we look at in this course. I'll say it again. Integration by parts is the last integration technique that we look at in this course. Now let's look at the example here. Example 1. Let's look at example 1 for integration by parts. We are integrating a function which is cos. Okay, we're integrating x multiplied by cos x with respect to x. So we're integrating x times cos x with respect to x. So we integrate the function x times cos x with respect to x. Okay, so this is the function that we're integrating. Now, for integration by parts, we have there's a specific formula that we use for this. So for integration by parts, there is a specific formula that we use for this. And the formula that we use for integration by parts is the following formula. So we integrate, and it's a formula. It's something that you must remember. All right, for integration by parts, we have a formula that you have to remember. It's not an identity. All right, it is not an identity, it's a formula. So for integration by parts, there's a specific formula that you guys have to remember. It is not an identity, it's a formula, and you have to remember this formula. Okay, I will not give this formula in the formula sheet. This is one formula that I will not give the formula sheet. It's something that you have to remember. So for integration by parts, the formula is the following. The integral of u with respect to v is equal to uv minus the integral of v du. It's a specific formula that you have to remember. Okay, the integration or the integral of u with respect to v is equal to uv minus the integral of v with respect to u. That's how it works. But I don't know. Okay, I'm thinking that maybe I should give it to you. Usually I don't give this formula, but I think I should give it. I think I should give it. Okay, I think I should give this formula. Yeah, I think I should give it. No, okay. All right. No, I'm gonna give it. So this formula here, I'm gonna give it to you guys. In the exam, I will give you this formula. So in the exam, I will give you guys this formula in the formula sheet. Okay, the integral of u with respect to v is equal to uv minus the integral of v with respect to u. So this is the formula that you use for the integration by parts. This is the integration by parts formula. Now, how do you apply it then? How do you use it in this case? Okay, so this is the formula for integration by parts. This is the integration by parts formula. So how do you apply this formula? How do you apply it? Now, you have this integral here. You've got x, the integral of x times cos x dx. You've got the integral of x times cos dx. If you look at this case here, if you look at this integral, you can see that you cannot apply the substitution rule here. And you can, again, you look at it, you see that there's a trig function multiplied by an algebraic function, which is x. So you can see already that you cannot apply even the trigonometric identity. You can't even use trigonometric substitution. So in that case, that hints that we have to use integration by parts, especially if you got two functions multiplied together like this. Okay, that hints us that we have to use the integration by parts. But how do you use it? Now the function that you multiplying by, this is x. So you got x times cos x. What we do is this: we let one of these functions be equal to u. Okay, so we're gonna do like this. We say let u be equal to one of these functions. So we're gonna say let u be, and you choose which one. But you must choose the appropriate one, because if you say let u be equal to cos x, okay, and you go ahead with it, you may find that you run into a problem. That it's not going to evaluate the way you want, or it's not going to simplify anything. So whether the integral simplifies when you are using the integration by parts technique, it depends on if you assign the appropriate if you assign your variables correctly. Okay, meaning that you must let u be equal to the proper function. You must let u be equal to the proper function and let dv be equal to the proper function. All right. For example, in this case, I'm going to let u be equal to x. So let u be equal to x. So you let u be equal to one of these functions here. You've got x times cos x, so you're going to let u be equal to one of them. So I choose to let u be equal to x. So let u be equal to x. Okay, so since I've let u be equal to x, now I must let u, I must let dv. So I basically assign u to one of these functions, and I also assign dv to the remainder of this integral, which is cos x dx. So I let u be equal to one of these functions, which is x, and then I let dv be equal to the remainder of the integral, which is cos x dx. So let u be equal to x, and also you let dv be equal to the remainder of that integral, which is cos x dx. So that's how it works. That's how integration by parts works. That's how you start. You start by letting u be equal to one of those functions, which is x, and then you let dv be equal to the remainder of the integral. In this case, it's cos x dx. And then after you do that, you move on in the following way. Since u is x, okay, you got u is x, you want to know what du is. So you go ahead and you calculate du. Now du dx, you basically just differentiate u with respect to x. Now du dx is equal to dx dx because u is x, which is just 1. So basically that implies that du is equal to dx. So you must write du in terms of dx. So after you assign u, so you say let u be equal to x, now you must write du in terms of dx by differentiating u with respect to x, like we did here. And then again, you've got dv is equal to cos x dx. The next thing you do now is that you integrate. You integrate both sides of this expression. So you integrate the left-hand side, which means you integrate dv, and that is equal to the integral of the right-hand side, which is cos x dx. Okay, and then the integral of dv, okay, or the integral, this is basically the integral of 1 dv. So if you're integrating dv, that's the integral of 1 dv. And if you're integrating 1, you're going to get v. Okay, so the integral of 1 dv is v. All right, so and so that's what you get on the left-hand side. On the right-hand side, you have the integral of cos x. So what do you differentiate to get cos x? Sine x. So the integral of the right-hand side is sine x. So meaning that v is equal to sine x. So which is our objective? Our objective is to find what v is. So you let u be equal to x. Okay, just give me a second. All right, so guys, now again, let me go through this again. This is how integration by parts works. The first thing you do, you let u, first of all, you're going to use this formula. This is the formula that you use. The integral of u dv is equal to uv minus the integral of v du. So that's the formula you use. You apply that formula. That's how, this is the formula. So for integration by parts, this is the formula that you apply. This is the formula that you use. How do you use this formula? You do like this. You're going to assign u to one of these functions here. Okay, in the integral, you're going to assign u to one of them, and then you're going to assign. So I'm going to say it again. You assign u to one of these functions here, and then you assign dv to the remainder. You assign dv to the remaining, or to what's remaining in the integral. because the integral contains x cos x dx. So you're going to assign u to one of these functions, and then you're going to assign dv to what's remaining in the integral after that. Okay, so basically what we decided to do in our case here, we decided to assign u to x. So we decided to assign u to x by saying let u be equal to x. And then after that, we then have the remaining thing in the integral is this, it's cos x dx, and that's what we assign to dv. So we assign dv to the remaining thing in the integral. Let me use a different color. We assign, so I'll say it again. Firstly, we assign u to one of the functions in the integral, which is x. We say let u be equal to x, so we did this. And then next, we assigned the remain what to we assigned what's remaining in the integral. We assigned that to dv. So we assign dv to what's remaining in the integral, which is this thing here. We assign dv to what's remaining in the integral, which is cos x dx, which is what we did here by saying let dv be equal to cos x dx. So that's what we do first. We start there with the integration by parts. We start by doing that, by assigning in this way. After we assign, we now want to know some things. We want to know what is du, and because we don't have du, we have u, but we don't have du. We have that u is equal to x, but we don't have what du is, and we need du. Because if you look here in the function here, if you look in the formula, you see a du here. So we need to know what this du is in terms of x. We want to know what is du in terms of x. We've got u in terms of x because u is equal to x, but what is du in terms of x? So that's what we need to find. All right. So that's why we do this. That's why we do this calculation here. That's why we do this calculation here, is to calculate and find out what du is in terms of x, because we don't have it. Again, we do have dv. dv, we have it. Here's dv here. dv in terms of x is equal to cos x dx. So we do have dv in terms of x, and we have that dv is equal to cos x dx. But then what is v? We don't have v. And we need v. We need v here, and we need v here. So we need to find out these things. We need to calculate them. So we have, this is so that we have every single thing that we need for this formula. So that we have every single thing we need for this formula to apply this formula for integration by parts. So we go ahead and then we calculate, we find, or we calculate, we go ahead and we calculate du. We calculate du. So we say let u be equal to x, and we differentiate. We say we differentiate u with respect to x, and we find that that's equal to 1 because du dx is equal to dx dx, which is equal to 1. And then we solve for du, and we basically get that du is equal to dx by multiplying through r by dx. So if you multiply through r by dx, if you say on the left hand side, if you go dx times this, and then you go dx times this, these dx's will cancel out, and then you got du, and then on the right hand side, you're gonna have dx. This is dx here. Yeah, no, this is bad writing. Let me just. So it's dx times this, and also dx times this. So cancel out these two dx's, you get du on the left, which is this. Sorry, go back. Which is this over here. And then you, on the right, you have dx. Okay. So that's how we find this du. So du basically, du in terms of x is equal to dx. So du is dx. And then now we have to find v. So to find v, integrate both sides of this expression. You got dv is equal to cos x dx. So integrate the left side, you get the integral of dv. On the right side, you have the integral of cos x dx. So you integrate both sides. On the left side, the integral of 1 dv, which is the integral of dv is the same as the integral of 1 dv, okay? Which is the same as, of course, if you integrate 1 dv, you get v, which is this over here. And then on the right-hand side, you integrate cos x dx. Now, the integral of cos x dx is sine x, because if you differentiate sine x, you get cos x. So then that's how, so you see now we have everything we need now. Now we have Now we have du. Okay, now we have du. Now we have du. Okay, now we have du, and du is this, and we also have v, and v is this. So now we have these things we need. We have everything we need for our integration by parts formula. What's left to do now is go ahead and is to go ahead and apply this integration by parts formula. So now what's left to do is to go ahead and apply this integration by parts formula. So let's go ahead and apply it. So we say therefore. Okay, let's use a black color for that. Black color for that. So we say, okay, therefore, now we're going to apply the integration by parts formula. We say therefore, the integral of u dv, and I'm going to say it like this. I'm going to say it like this. The formula says this. Let me write the formula down first. Okay. Let me write it down on this page. So the integral of u dv is equal to uv minus the integral of v du. Okay. Now, what does that mean? It means this. The integral. Now we said u is equal to x. So that's the integral of x multiplied, of course, by dv. Now dv, we said dv is equal to cos x dx. Okay, so the integral of u with respect to dv, sorry, the integral of u with respect to v is the same as the integral of x cos x dx, right? And then now, by our calculations here, we found that u, because we have to substitute. Okay, now let's see. Let's see. Now what we are doing here, we are applying the formula. The integral of u dv, is equal to uv minus the integral of v du. Now again, we said that u is x, so we put x there. dv is cos x dx. Okay, so that's how basically we fit this thing into the formula on the left side. Now on the right side, we need u. What is u? What did we say u is? Sorry, okay. We said u is x. We said let u be equal to x. So in place of u, then we put x, because everything must be in terms of x. So in place of u here, we're going to put x. Okay? In place of u, we put x. What about v? What's v? V, we had to calculate v by using this dv is equal to cos x dx expression. We used it to calculate v. So we found that v is equal to sine x in terms of x. It's sine x. So v in terms of x, we found it to be sine x. Okay, so we substitute in place of v, we put sine x. We go minus the integral of v. Again, the integral of v is sine x. So we put sine x again. Okay, with respect to u, which is du. Now du, what did we say about du? Well, we found out what du is from u is equal to x. We worked it out. We found that du is equal to dx. So we now substitute this du with a dx. So basically, we use this formula here and we substitute into the formula all these things that we have. Okay, on the left side, we substitute x cos x dx. On the right side, we've got u, v, which is x sine x, minus v du, which is sine x dx. So that's how you basically do it. That's how you go about it. And then now, we still have an integral to evaluate. We have to evaluate this integral here. What is the integral of sine x? And this integral here that we have to evaluate now is a much simpler integral than the main integral, which is this one here. It's a much simpler, and that's the whole point of the integration by parts, is to write your main integral, which is looks more complicated, and write it in terms of a much simpler integral that you can just simply evaluate. That's the whole point of this. So now we only have to evaluate this integral here, because it's much simpler. So the integral of sine x, what is it? What's the integral of sine x? What do you differentiate to get sine x? If you differentiate minus cos x, you will get sine x. So the integral of sine x is minus cos x. So this is equal to the following. It's equal to x multiplied by sine x minus cos x. Now, this is an indefinite integral, and you can put a plus c here at the end. All right. So this will be just minus is plus. So it's x sine x plus cos x plus your constant c, your arbitrary constant c. So this is the answer to this question. This is how you evaluate this integral by using integration by parts. This is how integration by parts works. It works like this. Now I'm gonna go. You can go ahead again, and you can go ahead and look at it again. You can go ahead, go back, and listen to this. Watch this explanation. You see, you can go back and watch this explanation. You see, and just practice this. Just practice it. You know, you'll find that it's simple. All right. Now, guys, again, if you let's say, for example, in this case, if you let u be equal to cos x, because sometimes you can let u because you like sometimes, you know, especially if you're not if you are not experienced in evaluating integrals using the integration by parts technique, you can sometimes let u be equal to the to, let's say, to cos x, like you can let it be equal to the function that will not simplify things, is what I'm trying to say. So if you're not experienced, sometimes you can let or you can make the mistake of letting u be equal to a function, or the function that will not simplify the integral. For example, in this case, if you let u be equal to cos x, letting u be equal to cos x and dv be equal to the remaining thing, which is x dx, and then going ahead and evaluating, it will not simplify your integral. You'll find that the integral that you have at the end is not a simplified integral. So now you would be forced to go back and let u be equal to x and dv be equal to cos x dx. So sometimes you do make that mistake sometimes, especially if you're not experienced in evaluating integrals with this technique. You can make the mistake of letting u be equal to the function in the integral that will not simplify things. If you find yourself doing that, just go back and start over again and let u be equal to the other function. All right. In this case, if we let u be equal to x and dv be equal to cos x dx, that simplifies things. And that makes it simple for us. It leads to a simpler integral, which is this integral here. And it gives us an answer quickly. Now, you can, if you want to, you can try and see. You can when you're practicing, you can let u be equal to cos x in this one and see what's going to happen. You see that you're going to get something that is going to lead to something that's not really simplified, and you're going to be forced to go back and let u be equal to x to evaluate the integral. Now, guys, let's look at the second example here. Example number 2. Now, example number 2. Again, we're going to apply our integration by parts technique. Now, let's look at what this one looks like. This one over here, we've got the integral of x multiplied by ln x with respect to x. So we've got the integral of x multiplied by ln x. Okay, we have the integral of x multiplied by ln x. I'll say it again. We have the integral of x multiplied by ln x with respect to x. If you look at this thing here, you can see that you can't apply the substitution rule. And it's not even a trigonometric function. You can't apply the trigonometric substitution. You know what I'm saying? So if you look at this thing, and there's also an x over here, it's just a hint that we over here with this one, we have to use integration by parts for this one. Now for this one, guys, if you let u, again, I'm going to write down the formula again. The formula for integration by parts is the following formula. It's the integral of x, sorry, no, the formula. The formula is the integral, is the integral of u respect to v is equal to uv minus the integral of v with respect to u. That's the formula we use. That's the integration by parts formula. All right. So now we have to let u be equal to something. So what are we going to assign u to? What are we going to assign u to? What are we going to assign u to? Now, if you go in this case, because integrals are different. So in this case, if you let u be equal to x, if you assign u to x in this case, if you assign u to x, if you assign u to x in this case, what is wrong with my thing here? Sorry. If you assign u to x in this case, and you assign dv to the remaining, which is ln x dx, you might have some problems. Okay, it might not evaluate. So for this one, it's more suitable to assign u to ln x. Again, if you have an exam, if you assign u to the wrong function, and you find that it doesn't simplify the integral, then go back and assign it to a different function. But in this case, it's better to assign u to ln x. In this case, it's better to assign u to ln x. So you can assign u. This thing doesn't work properly. Sorry, guys. Let me just go back. In this case, you assign u to this function here. You assign u to this function here. So assign u to ln x, and then you assign dv. You assign dv to the remaining thing there in the integral, which is x dx. So it's basically x is this one. Is this one here? X dx. So you assign u to ln x, and you assign dv to x dx. Okay, that's the way you do this one. So basically, you do like this. You say let u be equal to x. No. Sorry, that's a mistake. You say let u be equal to ln x. Let u be equal to ln x, and you say dv is equal to x dx. I hope I didn't make a mistake here by assigning, but I think I did it right. I think I assigned properly, because if I didn't assign properly, I'm gonna get an integral that's not really simplified. I'm gonna have to go back. But in this case, you let u be equal to ln x, and let dv be equal to x dx, and then you go ahead. So how do you go ahead? Now you've got u in terms of x, you've got dv in terms of x. You now have to find du in terms of x, because you need it in the formula. Remember, you need du here, and you also have to find v, in terms of x, because you need it here in the formula, over here and over here. So now we go ahead and we calculate these things. So we go, now u is ln x, so what's du? Okay, to get du, we differentiate u with respect to x. Now the derivative of u with respect to x is the same as the derivative of ln x with respect to x. Now the derivative of ln x with respect to x, you guys know it's 1 over x. Okay, it's 1 over x. So du dx is 1 over x. So what is du? So we just basically just multiply both sides by dx. Both sides by dx. The dx is cancelled out over here, you get du. So and on the right side, you basically just get 1 over x dx. Okay, so that's what you do. So this implies that du is basically equal to just 1 over x dx. So du is 1 over x dx. So that's what du is in terms of x. So now you've written du in terms of x. But now we want to know, what is v? What's v in terms of x? You get v in terms of x from this expression here. You get it from here by integrating this expression on the left side and the right side. So you say dv x dx, you integrate it. Integrate the left, integrate the right. Now on the left, you get v, as you saw before, you get v. And on the right, if you integrate x with respect to x, obviously, let me just write this. This is x over here. This x, it looks like a v in a way. Let me just make it clear that it is an x, it's not a v. Okay, it's an x, it's not a v. So let's put an x here. So on the right side here, you integrate x with respect to x, you are going to get x squared over 2. You don't put a plus c because you're still evaluating. It's not the main integral. This is not the main integral. So you don't put a plus c. So now we have v now. We have v. So we have v in terms of x. We've got du in terms of x and v in terms of x. So now we can go ahead and substitute using the integration by parts formula, which is this formula here. All right, this formula here, this one here. So now let's go to the next page and evaluate. So now we say therefore. Again, let's write the formula down. We've got u dv is equal to uv minus the integral of v du. Okay, now we're going to substitute into the formula. Now we said u is equal to ln x. We said u is equal to ln x. Okay, so in place of u we put ln x, like we said, put ln x, and then we say dv is x dx. Let's look. We said u is ln x, we put ln x. We said dv is x dx. So let's put it there. Okay, dv is x dx. You can put x dx there, no problem. Okay, or like we can write it as they presented it to us. We can put the x in front, but it's the same thing. You can put the x here, which is how they presented it to us. So, and let's write the dx closer. Okay, dx closer. So it is x ln x basically. And let me also write this thing like, let me write it again just to make it clear that it is x. It is x. This is x here. X ln x. So basically, so the integral of u dv is the integral of x ln x dx now. And in place of u, again, we said u is ln x. So in place of u, because now we have to substitute on the right now. So in place of u, we put ln x. So we put ln x. And in place of v, what is v? Let's all look. V we found to be x squared over 2. So in place of v, we're going to put x squared over 2. Come back and put x. We can put it here in front, or we can put it in the back. Let's put it here. X squared over 2. So x squared over 2 ln x. X squared over 2 ln x. That's uv. So uv is x squared over 2 ln x. When you write it in terms of x, it's x squared over 2 times ln x. And then we have minus the integral of v. Again, v is x squared. Let me just write it again. Okay, v is x squared over 2. That's v. What is du? Let's go check out what du is. Du is this. Du is 1 over x dx. Okay, so we go and we write it down. Du is 1 over x dx. We replace it, the du with 1 over x dx. So now you can see that the integral we have now is a much simpler one. There's no lns in the integral, no lns. It's a much simpler one. So now we have this is equal to x squared over 2 multiplied by ln x minus the integral. The two x's here will cancel, obviously, and that'll leave you with it'll leave you with x over 2. It'll leave you with x over 2 with respect to x. Okay, but then the 1 over 2 you can take it out as the 1 over 2 you can take it out. So you have 1 over 2 here, and you have x inside. Let me just fix that. Doesn't look good. It's you take out the 1 over 2, and inside you just have x. Okay, with respect to x. You see, it's a much simpler integral. And now, if you integrate obviously x with respect to x, you're gonna get x squared over 2. So now you end up with x squared over 2 multiplied by ln x minus 1 over 2 multiplied by x squared over 2. And you plus, obviously, you plus your arbitrary constant, which is c. Now, obviously, 1 over 2 times 1 over 2 is 1 over 4. So over here, you can just go ahead and just put 1 over 4 here. It's basically just, well, you can say, yeah, you just say it's x squared over 2 ln x minus x squared over 4 plus c. So guys, this is how the integration by parts works. This is how integration by parts works. And I think this lecture has been long enough. I think I must stop here. I can stop here. So guys, this is how integration by parts works. It works in this way. It's this is how you apply it. This is how you do it. Okay. Again, guys, go ahead and watch this video again. Watch the video again and study how these things work. And on Friday, this coming Friday, I'll give you guys a tutorial on this. I'll give you guys a tutorial on the integration techniques that we've just covered here in this lecture. Sorry, guys, if I'm speaking slow, or if I'm not, my words aren't as clear as usual. Yeah. Yes. Okay. So that's what it is. So guys, we can stop here for now. Well, we can stop here, like, you know, for the course, because as I said, this lecture is the last lecture of the course. So we stop here. This is all we're going to cover for the course, nothing else. As I said before, this coming Friday, I'll give you guys a tutorial just to practice these integration techniques, just to practice them. And then thereafter that, we can do a tutorial test or not. If you don't want it, we're not going to do it. So, but you will get a tutorial on this work this coming Friday, which is this, I think it's the second of June. Okay, this coming Friday is the 2nd of June. So on the 2nd of June, I'll give you guys a tutorial based on this work. Okay, guys, let's stop there. Thank you.